Camellia, I've got 12 o'clock. Shall we get started?
Absolutely.
Yeah, definitely.
All right. Well, welcome everyone. Good morning. On behalf of the Carolina chapter of SMRP, I'd like to welcome you to today's webinar. Today's speaker is Bill Frazier with UE Systems. And so, without further fanfare, I'm going to turn it over to him.
Thank you so much. It's a pleasure to be here. I'll share my screen in a minute. Really excited to be here and speak um, about a new generation of ultrasound. This is something we've been working on, and a little bit about my background. My name is Blair Fraser. I lead our technology at UE Systems. Um, and I can see some names here. And for those that do know me, my passion my background has been about where new technology and where AI really fits within I would say the reliability domain, but very specifically on the predictive maintenance domain. And my background came from industrial automation. I spent a number of years, decades even in industrial control, and I think that was the forte to AI. And for any of us that um, is on it came from the automation. We kind of grew up in fuzzy logic, neural networks, model predictive controls, and things like that. And that was at the forefront of artificial intelligence. Now, AI was there. It was something we were trying to implement, but it just wasn't. It wasn't at the level of where it is now. So what I'm going to talk about today is how with the rapid environment of change, and one thing that's clear is, especially in even the last few months, if this webinar had been in 2025, it would have been different content than it is today. And it's remiss if you're not watching the news, just the tech giants, the battle of artificial intelligence, and where that's going. And my job here is I am going to link it to ultrasound, but really, the concepts that I'm going to talk about here are universal. Ultrasound, vibration, thermography. I don't. It doesn't matter, right? What the intent here is to get thinking about how we can use this. And I'm going to go into two types of AI and just make sure that we understand the difference between the not we understand the difference because the reality is. From an AI point of view, I'm dangerously knowledgeable. I get the pleasure of over my career of working with some of the best data scientists in the world, and essentially got to ask a gazillion questions and sometimes the same one over and over again so I could understand. But just so we understand of what are the principles around machine learning. And then the other one is generative AI. And I think that's the one that most of us, if we're not using, we should be using. That is the chat GPTs, the co-pilots in Microsoft and things like that. So I'm going to get into that and how we can start to use that that technology. So just bear with me while I load this up. It has my Zoom has taken over my screen here. So just give me a second while I load this up and then I'll get into the presentation here. Correct. I promise you I did have everything teed up and then of course, I opened the browser and I lost it. Oh, okay. Now, as we go through this, I do apologize. This is meant to be interactive. It's meant to show kind of how we can use AI and how we can start thinking about it and how. Um, sorry, let me just bear with me here. I'll just make it a full screen view. This is the last time I have to do this, I promise you. Okay, can we see my screen?
I saw it shared for a bit and then it disappeared.
Same here.
Hmm. Okay. Well, let's see where that went. How about now? We're good?
I see it
Yes,
now.
I can see it now.
Excellent. Okay. So speaking of AI, maybe AI can help me run these webinars a little bit better. So we're going to talk generation of ultrasound. So just to ground everybody, I know this is SMRP, and most of us do not think of ultrasound, one of the primary technologies of bearing detection, leak detection, electrical arc flash detection. Just to make sure we're on the same ground. And and the reason why I do this now is actually AI related is the world is changing around search engines. So if you think about someone new that is going to be joining the SMRP or going to get their CMRP, they're going to start using tools like Google and start looking at things. They're going to type basic searches and, hey, what technology exists to help me detect bearings? And what they're going to get is answers from Google, for instance, which is no longer search engine optimization. It's going to be an AI response. And how that's going to learn is from content like this. So we do have to provide some background for it. When I'm talking about ultrasound, I'm not talking about NDT, and I'm not talking about medical imaging. This is about the ultrasound, or in the research in the academic world, it's called acoustic emissions, which is in the ultrasound domain. So just to set that standard. And um, I had the pleasure of um, co-founding an artificial intelligence company in the industrial space a number of years ago, and that gave me a great opportunity to learn. And it's actually where I first started to understand ultrasound. And one of the reasons I'm at UE Systems today is I believe that ultrasound is going to be one of the most valuable technologies to help us solve some of the world's toughest problems because of its ability to detect faults early and the ability to be able to listen inside of machines without actually physically going inside of those machines. And I do want to make it clear as we look at this is as we look at ultrasound and as I talk about ultrasound, a lot of what I'm going to talk about AI applies to vibration. It's a similar type of data in terms of time waveforms, FFT, enveloping, things like that. And I've often heard is, you know, ultrasound is just a really high frequency vibration, which yes, ultrasound measures high frequency vibration, but at the core root, the physics of ultrasound is completely different. I just want to make sure that's understood because as we start to use AI, we start to use machine learning or generative AI, we have to distinguish between the two. And I know many of us, grew up with a PDF curve, and as soon as you start to understand the PDF curve is for one fault, it's not a PDF curve across an entire asset. So ultrasound really works well at impacting the friction side of things, where vibration really does well with motion driven faults. And the reason that's becoming more clear is, um, for example, one of the sensors we have measures vibration and it measures ultrasound at the exact same time, and we can start to see there's certain aspects where vibration picks up faults a lot sooner than ultrasound, and there's a lot of times where ultrasound picks up faults sooner than vibration. It really depends on what you're trying to measure. Um, so what we're in this world now, and ultrasound has been around for decades and decades. UE System is entering its 34th year of using ultrasound, and it gives us the ability to listen to things that we can't hear. So it's not an audible range that we can't hear. And what the challenge is as our equipment becomes better at capturing that data, as the economies of scale allows ultrasound to be in more people's hands, it does allow us to collect more data. But the reality is what's happening is now we need to separate the noise from the value. And that's where I'm saying we need to shift from hearing, which is passive. Hearing just means sensor picks up everything. There's no filter, there's no noise. And that's including our ears. When we say hearing, we're passively train passing by, and our brain doesn't even, if you live by train tracks and a train is going by, your brain learns to take that noise out. That's actually listening. So what we want to do is start listening, start looking at extracting meaning from that sound that's coming in. Now, where I started to work with ultrasound and AI was being able to process hundreds of thousands of data points. And that's one thing that separates vibration in ultrasound, just because of the high frequency noise. And if anyone's familiar with the Nyquist, is you have to at least 2x, but often we're 10x, the sampling frequency of the fault we're trying to capture in basic terms. So at the low end, might be capturing around 22 to 25,000 samples per second. At the high end, up to 40, 50, 100 kilohertz. So we need to start sifting through that data. And when we talk about measuring ultrasound or acoustic emissions, we do pick up friction, but we can pick up electrical noise in a bearing. We can pick up other impacting. And I was at a conference recently, and someone described it very well, saying if you understand the physics, the mechanics behind your equipment, and you're using ultrasound, then you can understand what that data means. So noise is everywhere. What we need to do is start to look at what we need to focus in on. And if you just think about your plants, most of us that are end users have more than one bearing in our facility. So when we start to think about capturing thousands of data points per per thousands of data points per second and analyzing that, it becomes very cumbersome. And this is where AI is going to come in. And it's really going to help us determine where to look and how to look at all these data points coming in. The win is prioritization. It's not more noise. So this is, and if there's, I am going to leave time for Q&A, and by all means, what I'm saying is not meant to be absolute. This is just my experience and what we've been able to learn from the data. Every piece of research we do, and we've partnered with a number of universities across the globe of academics. All our research papers are public domain. If you ever want to see some of the research that we've been able to do, that we've been able to give to the market, and it'll help others train AI. This is a great one where we've done thousands of studies on bearings that have progressively failed. And I shouldn't say that. It sounds like we progressively failed 1,000 bearings. We progressively failed a few bearings and tracked thousands of data points across that failure curve. And what we're trying to see is these static calculations. And the reality is we operate in a variable world. Our loads change, our speeds change, our raw material can change, all that kind of stuff can change, but we often do these static calculations. And I grew up in this world, and especially on the vibration side, which does lead, a lot of these type of thinking to how we can process our data. And often you'll hear RMS, max RMS, peaks, crest factor, kurtosis, skewness, words like that. And what really happens and where AI is going to jump in, and this is my founding about, or my understanding from about 10 years ago, was the human brain can process 2 to 3 variables at a time and make sense of that. So what that means in the process world is my speed changed, my temperature changed, and my flow rate changed. And what was that correlation? What did it do to, say, my quality or my output? So 2 to 3. Now, some of us on this call might be able to do 4 to 5, right? But in reality, when we're doing those type of things, we're also adding what I would call a soft variable in our head. So if the temperature changed by 30 degrees, so that new is a delta. That's another variable we have to process in our head. So what we did is a study, and I call this condition stacking, is how well can we actually use the data from a single sample point that was taken traditionally on route-based data and look at kurtosis, look at crest factor, look at all these variables and actually make sense. In particularly, if we don't have the history of that, or we don't have the variables that change. And two things end up to be very true. And one is these types of variables in an industrial environment do fluctuate. So things like kurtosis, skewness, and I know they're very prominent in the vibration world. The variability does change in ultrasound. I'll tell you that where vibration has a tendency to be less influenced by load changes and speed changes. Now, if you're a vibration person, you're going, oh my gosh, no, it's not true. I just mean in relative to ultrasound. So what we found in a lab, those variables often work very, very well. They were designed to work on a sine wave. As we get into industry with other competing noise, if you ramp up your production and things like that, other noise can change that. And what we found is that condition stacking caused more issues than value, because you're often spending a lot of time trying to understand and going back into history. Well, what was my crest factor? What was my max RMS? And if you know crest factor, for example, it's RMS to the top peak, but as a fault keeps on continuing, that actually lessens. So you have to understand if you don't have the history and your crest factor is actually going down, you might actually be later in the failure curve. So that understanding is very valuable if you have time and if you have the training to do so. Otherwise, if you were to put in, and we know there's attrition issues with people coming into our industry, is if you don't have the history, you don't have the experience, it's very hard to use those variables and make sense of things. So this is where AI is really going to come in. Okay. And there is a whole world outside of machine learning and generative AI that is going to influence us in this space, but also our daily lives. And deep learning and things like that that I just don't want to get into, but these are the two most, in my opinion, the two most practical approaches that we can look at. Machine learning, where essentially you give it actually an output, and then it can learn from that data. Essentially, I call it a rules engine. It's going to create the rules it needs in order to get to that design output. So where we look at crest factor, kurtosis, and things like that, it can learn between the correlation and causation, the relationship between hundreds, thousands, billions of data points if needed from that point of view. And what we're working on at UE Systems, and I'll show you just to give you an idea of what this technology can do, is looking at from a mechanical application, looking at can we identify mechanical faults from lubrication faults. And if anyone knows ultrasound, it's getting very, very heavy use in condition-based lubrication, so determining when and how much grease is required. So I'll give you some examples of that. The next one is a generative AI or even agentic AI as you take it a step further where it actually completes the workflow and things like that. But I would say if you're not using generative AI, if you're at your office desk right now and you don't have some form, and I'm not recommending a Chat GPT versus Copilot versus Gore, like, all those ones, right? But if it's not being used in your daily life, is you are missing an opportunity. But as experts, we know that it can be very, very dangerous. And an example I give there is if you're an end user and you get a new motor coming into your facility, you could say, hey, here is this motor, build me an FMEA. And it will do exactly as you said. And it's going to give you an FMA like it knows 100% what it's doing, right? it the challenge is it didn't ask you context. Is this inside? Is it outside? I reside in Toronto, in Ontario, Canada, and we had minus with the wind chill, we had minus 50 degrees C. So you start to think if it doesn't know that context, that FMEA completely changes. But in its world, it's completely right. Right. So we have to start thinking about how we use this, how we put guide rails. And I'm going to give you 5 frameworks to look at. It's not related to UE systems. It's not related to ultrasound, but just some 5 things to think about as you're looking at generative AI within your operations. So ultrasound and AI, what can ML do? And there's a few things that are going to be very, very important. And I think this is where ultrasound is really going to set itself apart. So with ultrasound is we just any kind of mechanical device just needs to create friction. And if you think of things like linear bearings, ball screw actuators, things like that that don't necessarily move in the vibration world, is we can start to pick those up in ultrasound. The challenge is everyone is unique. There's no set, ISO standard saying if it hits this ultrasound level, we need to do something. So I believe, and there's a lot of frameworks out there that suggest this is well, everyone wants to get to this remaining useful life. Like, tell me exactly when this piece of equipment is going to fail, and tell me what I need to do to prevent it. Sure, let's get to that place, and I have no doubt we will over time. But if you have thousands, hundreds or thousands of assets, and you have very critical, complicated assets that might not fall into the traditional technology approach, what if it was just to tell you that something's different, that something is behaving different, and you as an expert need to go in there and look at it more. And I think just stopping at that piece of the AI value chain can provide a lot of value, right? So it's not telling you when it's going to fail. It's not even going to tell you why it's failing. It's going to say out of these variables, this is what's leading to it to be anomaly. I'm making this up. It's the number of peaks or the overall energy or things like that, but at least it gives you some guidance in a world where often our most critical assets are the most complex. Just telling domain experts that something's wrong could be um, uh, a very good advantage. And then we have classification. And again, I'm summarizing this, and you want to look at pattern recognition versus ML, and we can get into that debate. But and pattern recognition is not machine learning, but is what we're doing again. This pattern represents a bearing issue versus lubrication, and getting smarter over time with that reinforcement learning. And one of the things I think is going to have a big, big change on our industry across all technologies, across the operations domain as well, it is more and more motors, for example, are operating on VFDs. They're asked to do more in a wider range of speed and load because raw inventory, raw stock is changing, raw outputs have to be throttled down. Is identifying operating states is often in condition monitoring. We're told to take the data with the same conditions every time. And that is, from what I'm seeing from working with our customers, is that's becoming more and more of a challenge to say, hey, operations, can you run this at this load and this speed? The world's just not going to be able to work like that anymore. And can we have a world where AI is helping us identify this operating state so we have a moving baseline, we have moving alerts, right? And I call those dynamic. And that's all what's being implemented now with this type of technology. So I want to walk you through AI that enables decision intelligence, and what I'm talking about here today in the next 3.5 hours, if I keep going at this pace, but is in my opinion. So let's not even talking about the the models, the algorithms, and there's a difference between a model and algorithm and all that kind of stuff. But generally, just the term of we need AI to help us make better decisions and help us be more efficient and effective with our jobs. If we solve those two problems, I think we're going to have better success at realizing the reliability of our facilities. So, what we've been working on, and this has been a labor of love for a number of years, is taking that ultrasound time waveform. And some of the things I'm going to show you is what ultrasound, and I mentioned this earlier, does become more variable than vibration. And in vibration world, you have millivolts per Gs and things like that. With ultrasound, you have different mounting techniques, you have different frequencies that UE Systems has that allows us to move the frequency tuning to remove some noise. You can have different attachments, and all that can change the fundamental way that the time waveform looks. And we need to be able to account for that. And so what we've been able to build is a patented AI algorithm that looks at that can start to normalize that data. And I'll give you an example of what that looks like. And then we can process that data, and we can start to look at that data and look at the peaks, and filter that data out to say, hey, this is more than likely a mechanical issue, or this is more than likely a lubrication issue. And if you just hover on the words I said, more than likely, right? And I think this is where we got to be very careful, especially as we get to, um, you know, call it chatbots, if you will, but you know, more than likely. And what we've been able to build is case studies. Is yes, this looks very, very similar. And the way I would analogy is like case law in lawyers is there's a previous example of where this resulted in that output, and that's what we're looking towards, right? So what we have is we can process that information and say, hey, this is more likely a mechanical issue or a lubrication issue. And what it's giving you is that decision intelligence, right? It's giving you that ability to say, okay, I need to lubricate, or I need to do some kind of preventative action with that bearing based on the criticality and things like that. So let's walk through that scenario. So let's look like before greasing, and this is a representative, is we're taking that time waveform in real time, we're processing that data with an AI algorithm. So that AI has been trained in the cloud. It's to train a model is very resource intensive. You need a lot of data processing power, but the time you can run AI at the edge, it becomes very efficient, and sometimes to be able to run that at the edge. So our sensor that's part of our on track can process this data right at the edge or in the gateway. And so what it's doing is processing that data, and it's looking like, oh my gosh, before greasing, I have a lubrication issue and I have a mechanical issue. And one thing we found is having both is very, very common. So the minute you start to apply grease, you start to see that lubrication issue, that lubrication start to go down. Why? Well, the peaks are going down. Lubrication is very it's like little explosions, so those peaks are all over the place where mechanical issues become very synchronous because of the way the bearing spins and all that kind of stuff. So as grease starts to get applied, that lubrication issue goes down. And once it's fully greased, is you may have that lubrication issue um, resolved, but that mechanical issue isn't there, right? And we have found this from the on-track system of there's about 1,000 lubrication events happening every month, and we've seen that number of times where lubrication issue can um, temporarily mask a failure, but it's never going to eliminate that failure. And I'm convinced to this day that grease usage, if done accurately, is going to be one very important health indicator we will start to see in our condition-based for mechanical equipment in our condition-based monitoring programs. And I'll say that again and I'll show you examples of that is grease usage of how much grease is being used. And if that's increasing is going to be a good indication of the health of that bearing. All right. So grease fixes the issue, but impacts remain. So there's still some level of mechanical issue in that. So that gives you an idea of what machine learning can do. Now I want to get into generative AI, and this is something that we're releasing out, and I'll show you what it looks like. Is UE1 Copilot. This is a agent, if you will, in a world of agents. When we're talking to more machines than people these days, is we built an agent to help our customers scale. It is not meant to replace them. It's not meant to replace proper ISO level certification, the experience, the mentorship of people that have been there before. But for those that just need guidance, they need someone to chat to, they need someone to learn with them. We believe that this tool and the use of this type of AI is really going to change the game. So what we've been able to do is essentially train AI on what we know, on what we've been able to experience, what we've been able to learn. That includes the formal theory of teaching of how ultrasound works, structure-borne, airborne ultrasound, the different effects of sensitivity and frequency and things like that. And we've also been able to give it context of thousands of case studies of things that have worked and things that haven't, and those type of things. And it's been able to ingest that. But more importantly, we've been able to give it some guide rails. We've been able to say, hey, if you don't know, don't ask. So if you give it ultrasound data and it has no context to it and say, hey, did this improve over time? And you don't tell it its sensitivity, or you don't tell it how you acquired it, it's going to say, yeah, just looking at the data, sure, the overall amplitudes have decreased, but you don't give me enough information, right? So we've trained it to make sure it doesn't hallucinate and to not give guidance. And one thing is certain: it's never going to tell you to replace a bearing. That is entirely up to you as the owner of this type of thing. So what I'm going to walk you through is this is how we looked at creating this UE1 Copilot, but I'll give you an idea of how you can start to think about this, and whether it's in your personal life or whether it's using this ultrasound Copilot as a way to change the game with ultrasound. So there's 5 mental models that are out there, and I think they're very important as we look at, will this Copilot even do anything for you? Is it a value for you, right? So let me walk through this. So this one talks about bottlenecks. Essentially, your biggest bottlenecks is going to set the pace for how this AI is going to work. And you can automate the analysis all you want, but if you still have to print out a report and hand it to somebody, the backlog is going to be probably be printing out at the printer versus actually doing the analysis and things like that. Now you might have different job functions, and that's no longer in your court. But that's something I would ask you to consider is when you start to look at this, is the slowest part of the system sets the pace for automation, sets the pace for AI. So when you're looking at this, and as I'm talking about analysis and using AI to help analysis, if there's slower parts in the process than the analysis piece, is you really need to address that up front. Oh, this is a good one. Essentially, the simplest solution is typically the best, right? Is spreadsheets, lookup tables, all that kind of stuff. Can a simple API call do that? And the analogy I'm going to give you, and I can show you this, or you can experiment if you want access to it, is so let's take a predictive maintenance program and you're setting it up and you collect data, you don't have bearing information, which is common. And it's on a motor. Well, most motor known plates have the bearing number. Now, what bearing could be in there versus the bearing number of the nameplate, I understand could be different, right? But instead of sending someone out there, could you go and grab a picture and just throw it into this Copilot and ask, get me the bearing numbers from this? Absolutely, right? Probably the simplest answer. So just remember the simplest solution that works is usually the right one. This is very interesting. So if you grew up in the automation world, they usually used to say the old way of thinking was if there wasn't at least 10x better productivity to switch to something new, it wasn't worth it. So 10x. So it had to be, if you improved any kind of process, and this I'm talking about analyzing data, but if you improved any kind of process by 2%, 2x, 3x, yes. But what the study shows, you needed about 10x to actually drive that forward. So now the question is with this type of AI is let's reframe that. If you had 100 helpers in your day to day, and I'm talking about um, this process is what would you do with them, right? And I often say is where AI seems to be focusing is taking a lot of the creative side of who we are as humans away. Where the joke is I'd rather AI do my laundry than create PowerPoint presentations for me because I actually like it, right? So we have to think about how you would use 100 helpers, and that's what AI in terms of these copilots are. They're helpers. Um, so frequency has a set cost. So the frequency of how you do things. So let me walk you through this. So if you are only analyzing 6 bearings a month, and there's a better way to do this, it's probably not going to pay for itself, right? When this type of technology comes in, and just think about it just in your life with Chat GPT or things like that, there's a minimum level we have to cross before it starts to pay for itself. So if you're just analyzing 6, investing in the time and all that kind of stuff to do this type of technology is not going to make sense, right? You want to get to the point where you're hitting that lower threshold limit to automation. And this is the last one, and this is where I'd recommend, and this is a fundamental learning that I've applied to all business, is often we look at and we talk about a lot in reliability is root cause analysis. So what happened and what can we do to prevent it? The thinking has changed to a pre-mortem. And it's not how is this going to work? It's how could this co-pilot fail in the future? So picture yourself 6 months down the road, it failed. Why did it fail? Why did adoption? Why did this co-pilot fail? And it can be, well, we didn't train people on what it is. People don't understand how it learned. How is it making recommendations? You think I'm going to trust something that just spits out an answer without giving me background so those are the things that are going to start to really affect us. And those are the 5 models that we went through to create this is addressing where most of these ones fail, right? And you got to keep in mind, like a Chat GPT is generative. Like most of its learning comes from sites like Reddit, where it's us giving it information, right? So this is can become very, very important. And this is where I'm hoping we can have a discussion on is how do these chatbots fail, right? And I can tell you, and it's no different than a lot of you that implemented, and and once in my life it was an end user as well, is often you get one kick at the can. If you put technology in and it bites you in the butt, it's very hard to overcome that in the future. So getting that right and addressing that up front is going to be very, very important. All right, so what I'm going to show you now, and I'm going to be flipping screens, so bear with me, is how AI can come into our daily workflow. The situation I'm going to give you is after data is collected. So we've already collected this data, and we need to start analyzing this data and making sense of it and driving action from it. Okay, so the first thing I'm going to show you, and let me find my mouse here. Let me just make sure. I am going to share sound here temporarily, then I'll turn it back off. So if you do hear my other screen with Teams and Outlook dinging, I apologize, but I'm sharing sound here. Um, so this here is the new UE1 analyzer tool. As you can see here, we have our integrated UE1 Copilot. So the first thing I want to talk about is ultrasound has always been qualitative. It sounds like and hearing. And that human interpretation of data is very, very important. I don't think as we get to AI that we lose that because that is something that's fundamental at the human level. What we need to do is look at the way we say it sounds like to quantitative measures, right? And if we can interpret that as it sounds like impacting, it sounds like this, there is a mathematical way we can represent that signal, and AI is going to help us do that. So what I'm going to do is I'm just going to play this signal. Now I'm hoping you guys were able to hear that. Now, if I wanted to, I could play it back faster, and it sounds like Alvin and the Chipmunks. So I do have a preloaded data set, and I'll show you where it came from. This is before and after lubrication. So if I look at after lubrication and play it, and then play that. Okay, so it sounds very familiar. And lubrication is you're expecting, but let me share with you where this came from. Okay, so this was sound files I captured today. So this is live data coming in, and I thought I'd grab the most recent. This is on a Boulder feed water pump. This is the friction level. Obviously, it starts and stops. And what happened here is I lubricated that bearing. So if you look down here, I lubricated it at 10:53 this morning. If you're doing the math, yes, that was an hour before this webinar, and I understand what I was doing there. I used assist mode, so what it did is it automatically lubricated with the guardrails in place. It put in almost 1 cc or 1 ounce of grease in. It dropped the friction from 60 dB down to 54 dB. Why is that important? Well, 6 dB is about double the friction level. So right here you can see we took that friction, I added grease, and that dropped. That was the sound you heard before and after. All right. So so just so you have context to what we're sharing here. So the first thing we did there is we just listened to a bearing. What I want to show you next is how do we compare things equally? And that's where AI is really going to start to help us. So as we look at comparing things with the new signal analyzer tool we have is I can do things now, and I'm telling you the rate at which technology and which software is going to grow and is going to change weekly what are able to do. So let me just overlay. So now I'm overlaying those two images. I'm overlaying before and after. And if you were to look at this, and I'll make it a little bit bigger for you, if you were to look at this, you can see, yes, the orange is after, the blue is before, so that overall energy. But what I can do now, click of a button, and our sensors are doing this automatically for that lubrication detection versus mechanical faults, is I can start to normalize that sensitivity. So what it does is it puts everything at the same level, right? So it takes all the variability off of ultrasound. Now I can see the true change of that. So while I could hear stuff audibly, right, now we can start to look at that with the help of the data and start to see things in a different context. So we're about sensitivity. So now we're apples to apples, right? And you might have done this in the vibration world to, so much millivolts per G, and then you've had to change the range to match it for other types of sensors and things like that. So even in the world of time waveforms, FFTs and filter bands, is yes, it's not AI. Yes, there's essentially fundamental first principle models that we can follow. And technically, and there was a time where everything was AI, like a vacuum cleaner was AI, and technically, if you create a rule and it executes on it, sure, that's artificial intelligence, right? But even just the way we can start to look at data. We can start to transform that data. So with spectrum analysis and things like that, is we can start to look at that data and enter it in ways that maybe we haven't before quickly. So calculating peak to peaks, and you notice here, we can start to look at each waveform and zero to peaks with a click of a button. We can rearrange that data. Now, I'm not going to um, go into a lot of detail here, but let's just say these spikes I didn't want here. I'm like, yeah, those spikes are process related. Um, and I'm making this up, but then, just going in, and this is where the power is going to come in is let me just select that. So that's at, what, 1.4. So let's just pick here, 70. So I can go 70 hertz, and this is going to fundamentally transform this. But just go through and just cut that where I knew that noise was coming in. Let's just cut that piece out. So I've cut that out. All my data now has that piece out of that. And I know if you're in the vibration world, like it's notch filtering and all that kind of stuff, but this type of technology is coming to ultrasound with the click of a button. So now I have this new waveform, which I don't want anymore because I just arbitrarily picked a number from that point of view, right? So the way we can look at data, the way we can process data. And what I'll show you next, instead of changing screens, is how can we use AI just to help us? So a lot of the times, our customers will just message us, "Hey, I have this sound file. Essentially, a sound file is a time waveform. Can you help analyze this?" And we get an email. I'm like, "What we're doing? Can you give me some context?" Right? But even no matter the context, if it's mechanical, you're going to do certain things as an analyst. And just with a click of a button, hitting auto, we can start to go and look at it's just going to go through and here's the top three harmonic families that I'm seeing. I don't know anything about it, and here's the top five spectrum peaks, right? So I can just go start to look into that automatically and just start to look in. Say, what are those peaks telling me? And I can quickly go in here and let me just say, and I'm making this up. Hey, this is I don't know why I picked electrical. That was probably a bad example. Right. And I can flag that as being electrical. Hey, you haven't, but even just as analysis, you're starting to look at this. Just give me some recommendations of where to start looking. So is it going to change the game? Is it going, should you shut down equipment, replace bearings based on this? No, but it starts to guide you in the world of mechanical of where to start looking from that perspective. And then, so let's take it a little bit further here. So I'm going to go back. We'll catch up on this. Is the rule-based automation. So that's where it's looking for the top harmonics. It's looking to give you some information, right? And again, this isn't game-changing from that point of view. Like these types of rules have existed, right? One times, two times, peaks, all that type of stuff. But being able to implement them and interact with them real time, I think has changed, right? Now, what I'm going to get to you, and really what I believe is going to change the game, and this is going to be across the board from all technologies. This isn't meant to be, just about UE systems, but I really have no way of showing this other than showing the platform. So, what we're going to get into next is looking at this and saying, yes, okay, I've seen some of this, the auto, I see some peaks, I see repetitiveness, whatever it is. And by the way, I'm a big fan of light mode. All software seems to have a light mode and dark mode, and that's coming with the new generation of people coming in. I prefer light mode, but I think this is how I grew up, so I'm learning to love the dark mode. But now we can start to open UE1 Copilot. This is where the game is going to change. So we have this information. In this case, this came from our 950 sensors, which is our wireless ultrasound and vibration data. So we're very lucky that if you just look at this file name, I get the asset name, I get the kilohertz it was taken at. As we remember, UE systems, we can change that frequency to move it along that response curve. We also get the sensitivity. So I can just do something like this, analyze the spectrum. And this is happening in real time. So I do apologize. It does take a while. It's not instant. Um, but what it's going to do is it's going to analyze it like um, a good trained analyst would do. Remember, I haven't given a lot of context. Um, so this is before and after. So it's telling us where um, the the frequencies are. And if you look at this, I've labeled it pre-loop and post-loop, so it can look at the file name. But essentially, what it's saying is like, listen, you haven't given me the RPM, right? I can tell you something, but I haven't given you the RPM, right? So it's like, okay, I don't. Let me go look up the RPM. I'm going to go look up the RPM, but let's just see if I can find some defect patterns. And these are just preemptive prompts. You can type things in. Right? And what's important here is it's been trained, right? So it's going to give you, if you notice, what we've trained it to do is to give you the supporting information why it's um, giving you this information, right? So the last thing we didn't want to do was say, "Yep, looks like a bearing defect." You're like, well, what? Why? Right? So it tells us to detect potential bearing defects, I'll examine the signal one and signal two, envelope spectrum, any signs of asynchronous non da, 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 da. I know you can read this. So here, since the bearing model and RPM haven't been confirmed, we won't be able to precisely calculate this. So we've trained it to be open and honest. And I'll jokingly say, be very Canadian-like. Be polite, but say, hey, I don't have enough information. Right? And it's going to go through. So da da da. So what I can say is, let me enter and I'm making this up. Okay, well I got the RPM, and it's gonna start to look at it. Right? Considering the observation, the presence of asynchronous frequencies, blah 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 blah. Right? Let me picture. So let's just say I've taken it that far. Right. And I'm hoping, and if you can think about if you're like an expert on condition monitoring, you're going through this, you're like, I don't need this, and that's absolutely fine. Right. But I do believe that just being able to, especially in your junior and your workflow, being able to have this as you're building your program and things like that's going to be very important. So now let's go through and let me take these cursors off. And you know what? I do know the bearing number. Oh, John went out and looked in their CMS and gave me the bearing number. And I'm making this up. Let's go through and start to look at this. And I'm going to say it's oh gosh, let's say it's an SKF 212, which is just I mean, I'd be very lucky if I was, right? But let's go start to look at these and look at the bearing the specific bearing fault frequencies in this, right? And let me just go back and say, oh yeah, again, obviously I'm not really seeing much in this. But I can go back. This is a SKF. What did I say it was? 217, just to keep consistent. 217 there. So all the database is loaded in the analysis tool. It's also loaded, and you can see there, I think it was like 88,000. And I hope bearing companies keep on producing new bearings that are better, that are more efficient and all that kind of stuff. So as that grows, this is where it's linked to a live database as it comes in. So now it can kind of give us this type of information. And then what I can do now is when we start to think about the automation is, okay, I need to give this to operations who's not technical, create it doesn't help with my spelling, a summary that I can give to operations. And I'm making this up, obviously, right? But now we're going just beyond the analysis piece and we're giving it to help just put this into language that we might not say here. So we've conducted analysis of this bearing, key findings, next step, right? I can go add this to my notes. It's now in my notes. I can go and export a report, and you're not going to be able to see it pop up in a different window. But even just that is information enough. Or create the description for a work order, and I will paste it into Maximo. I'm picking Maximo for no other reason, right? But you can imagine a world where this is connected through APIs and boom, create a notification and off to Maximo it goes with this type of information, right? So there we go. Work order description for Maximo. Again, early stages, but I think it's important of how we're changing the game with this type of technology and how we can really think about um, how this interacts with our workflow. So I'm hoping you got some takeaways from that. And what's key to know is the guardrails and safe use of this. So ask for missing inputs. So assumptions and it's always going to tell you that. Never confirm a fault without verification, right? And I can promise you this is anything that comes out of UE systems, it's never going to give you an overall um, asset level health. I fundamentally this ultrasound is one technology. I'm going to give you an example. Misalignment is yes, we can ingest vibration data into that platform as well. And it says as our 950 takes data at the same time from both technologies. So we can actually ask it, say, derive the estimated RPM if I don't know it from the vibration, from the velocity, from the one times velocity, and then we can apply that to the ultrasound signal, right? But it's never going to say, hey, go replace this bearing or your asset health is 50% because we don't see the other technologies, right? We don't see certain things, right? So it's always going to give you as the domain experts the guidance from what it knows. And if we don't train AI that way, then that's where we get in hallucinations where AI can be very, very confident and very, very wrong at the same time. So what I'll do here is I think I got 9 minutes left of this. So I covered kind of how we're using it, machine learning, generative AI. What I will do is open it up for questions. Camille, I'm not sure quite how it works, but I'll just pause here, and if I'll take a look at the chat too while we're talking, if anyone has any specific questions. Okay, I see some. Okay, I see some questions. I believe this is recorded, as Camille told me, and on the SMRP body of knowledge, which is going to be great. And I hope this feeds into AI at some point. You have a bearing on a component shaft. The shaft's attached to a drive motor. If you're coupling, how do you isolate the bearing? You want to test to filter out the noise from other variables, motor shaft. Oh, okay. So absolutely. And this is where domain expertise comes in because, ultrasound can be used to detect a coupling issue, particularly at lower speeds, but then that sound will absolutely propagate into the bearing. And if you have them very close on pillow blocks, if you have one defect, that can go to the other one. So you do need some domain expertise and giving it asset context. And what we like to do in this Copilot now is to take readings from both. So here's the readings from the drive end, the non-drive end, the coupling, those type of things. And it can look at it. Okay, I see a high harmonics, a high resonance at this section on this bearing. I also see it a little bit on this one. It's likely this one. Let me take this out, and what do I see? So there's practices to look at that from doing that. Um, da, da, da. Okay, Buddy. So overall, he's nearly correct. I do have an issue with him saying Amylin is rule based. 100%, 100%. I didn't mean like that from a true physics point of view. So Buddy, you are way more trained on me. I'm just dumbing it down honestly to my level as an engineer in automation and controls about what it's doing. But and there are way more experts out this on machine learning. I'm just trying to simplify the concept. So agree 100%. Ultrasound is only used on bearings for any equipment that changes sound. No, so ultrasound is used to essentially the ultrasound is measured in a decibel level, and that's directly correlated to the friction or impacting in that bearing. So it doesn't necessarily need to change sound. Is you're listening to what's happening inside. Okay. And Patrick, I'm confused. Your autocorrelation graph, no sim correlation with the BPF, no information. It was 0.8 or better data in the. Yeah. So again, I was just fat fingering numbers and examples and all that kind of stuff. The real truth is going to be when you start to use it and how you start to use that with the autocorrelations and things like that. So it will work better on. But here's the reality: is this tool that we created that I showcased last week has got infinitely better than it was the day before, and we actually designed this tool for internal use, and then we started to realize that there's a need for it in the market as we build up our own expertise and things like that. So, is it perfect? I'm not 100% no, right? Still, there's still days where, oh, actually, it was kind of wrong on this, right? And that's where I'm going to suggest you use AI with caution, right? Is it's learning. Make sure we need domain expertise to look at it. Um, so about getting data in, and I think no, thank you, buddy, for your comment there as well. About getting data into CMMSs, and I'm going to go on a diatribe here. Is you will not find, and I'm being very, very open and honest with this, is you'll not find. I'll make this big so you can see me. You'll not find a software company out there that says we can't get data into anything. Like there's Zapier, there's way of force feeding. I'm pretty sure data from an abacus manually moved into platforms now. But really, the is how native is it? How those connections exist. So if anyone is building software, and this is anyone in our industry is building software now to connect to CMMSs, to connect to that data through APIs, through GraphQLs, and it should be easy to do. And no one should say data connection is proprietary, but if you're working with someone that says, okay, let's get data into here, and I got a 6 months project, and let's get that data in, I would challenge that. But data connection should no longer be a competitor differentiator in the marketplace. Everyone should be able to connect to everyone and everything, and that's how I fully believe that there's no one company that's going to own all the data. This idea of this, I'm going to have all your master data and tell you everything. It's going to come from all corners of the plant, all corners of the levels, and they're going to integrate. There's going to be data lakes, but there's never going to be one kind of master of record until we get kind of the more into. I don't want to get into unified namespace and things like that and my beliefs on that. But anyways, so uh, I don't see any new questions pop up. In terms of this, it wasn't meant to be commercial. If you do want to connect with me and maybe drive it, you're more than welcome to reach out to me on LinkedIn. Blair Fraser, UE Systems, just connect with me on LinkedIn. My email address is Blair, BLAIRF at uesystems.com. Feel free to reach out. Again, this was meant to be agnostic, but if you have ideas or discussions you want to continue. And again, dangerously knowledgeable in AI. The only way I've learned this is through hard knocks. So I can sit here all day and tell you what not to do. I can't tell you really what you really should be doing across the board. These are just my opinions and where I've failed in my implementation of AI. So thank you so much. Thank you, Phil, for inviting me on this, and I hope everyone took at least something away from this.
Well, again, thank you, Blair, for presenting today. It's very insightful. I do want to thank everyone for joining us today and be on the lookout for a webinar for next month. Camille, do you have anything to add?
Nope, that's it. Thank you all for joining today.
Have a good day, everyone.